Welcome dear students, we are in the series of quantum technology, and in this series now we are discussing the quantum energy storage devices. In the quantum energy storage devices, because of the today's need, we will discuss the new topic, which is a flexible quantum energy storage devices. That includes the quantum batteries, advanced flexible supercapacitor, which represent a frontier in the power storage for wearable and the portable electronics. So, they offer the high speed charging, long cycle life and high power densities by utilizing quantum principle. What quantum principle they use? They use the superposition and entanglement alongside deformable architectures to enable flexible, lightweight and shape comfortable power sources. So, to fabricate flexible electrodes, various materials use, means various material in the form of the substrate we use. So, to fabricate flexible electrodes, stainless steel grids, lithium foil, nickel foil have been used as the conductive substrates. So, the major drawback of using these substrates is that they corrode on exposure of liquid electrolytes over the time. So, they prevent from the electrode, and which restricts the lifetime of the devices. So, we use these type of substrate. Moreover, the use of the metallic current collectors have a negative impact as they weigh and increase the total weight of the supercapacitor devices. So, impacting the specific energy and the power densities. So, therefore, the research is towards the design of the lightweight non-metal materials as current collectors for the flexible supercapacitor electrodes. So, this has been a potential shift towards the two-dimensional nanomaterials, including the graphene, magazines and transitions metals, dichalcogenides since 2018. So, due to their high surface area and mechanical flexibility. So, two-dimensional material we use for the fabrication of the quantum flexible electronic storage devices. So, these materials have been made new design, including fiber shaped, and moreover they are stretchable and textile integrated supercapacitors, and they are having a good capacitance even under the mechanical strain. So, an exceptional two-dimensional transition metals, carbides and nitrides are the are like magazine, which have rich surface chemistry, metallic conductivity, high surface area, and they are good mechanical strength materials. So, this has contributed enormously to the development of wearable energy storage devices in the form of supercapacitor. So, incorporating of the magazine based composites into the flexible, lightweight and wearable textiles, enhancing electrochemical performance without compromising wearability. So, at any stretch, at any wearable material, we can use this magazine so that we can develop a fast charging and low discharging quantum mechanical devices. So, optimization has also focused on the solid state electrolytes and the micro supercapacitors architectures to improve safety and energy density in the compact form of the factors. Concurrent with this development is the device is derived for the biocompatible wearable supercapacitor that can be used in the biomedical applications. So, especially for uses in on-skin electronics, e-health monitoring and implanting devices, we can use these chargeable supercapacitors. So, challenges remains particularly with the biocompatibility and the skin irritation, as many high performance material that has been used for the fabrication of the supercapacitor, there are certain metal oxide are must be toxic free. So, recent research is focused on the natural polymer based electrolytes and biodegradable substances to address these concerns. So, moreover, researchers have emphasized textile based platforms using conductive fibers utilizing PDOT. So, PSS coated yarn or carbonized cotton to build the seamless energy storage devices that blend with the clothing, as well as they can be wearable, they can be stretchable, they can be work in a various parameters. So, the primary steps is developing a smart textile is to make a conductive textile, which is made either by converting a conventional textile into a conductive material by inserting thin metal fibers, that is yarns, or by anti-static treatments. So, these other possible ways is to treat the textile with conductive ink at the fiber. Moreover, we can print on the fiber or we can print on the any cloth or any textile material like the yarn, fabric or the polymer levels. So, from a technological point of view, it is essential to maintain the flexibility, and as coated with the metal nanoparticles could give high conductivity. However, it may come at the expense of the flexibility and lack of durability. Ensuring mechanical durability, washability and long-term skin compatibility continue to be a major barrier to commercialization. So, there are the various parameters we have to keep in mind whenever we just preparing the wearable or we can say flexible supercapacitors or any energy storage devices. So, advanced electrodes, various electrodes materials are used for the wearable supercapacitors to meet the specific requirements and optimize the device's performances for wearable application. If what we are preparing the flexible, that flexible must be wearable, that must be stretchable, that having the various advantages regarding the optimization as well as the performance of these in the wearable application, in the medical applications or in the various e-medical services or a biodegradable material. So, advanced electrode we can use for the preparation of the supercapacitor. So, advanced electrodes, various electrodes materials we will use that must be suitable for the wearable supercapacitors, so that we can get the application requirements and it can be optimized the device's performance for the wearable application. So, there are the different electrode materials which we can use for the wearable supercapacitors. So, to achieve the different properties and the performance characteristics. So, key factors such as specific capacitance, cycle stability, conductivity and the flexibility influences the choice of electrode material. Now we are preparing the flexible electrode. So, choice of the material in such a sense so that we can get the specific factors like specific capacitance, cycle stability, conductivity, flexibility. These are the various parameters whenever we are just preparing the flexible electronic storage devices. So, the choice of the electrode materials for a particular wearable supercapacitor applications will depend on the specific requirement that for the particular applications. Like wearable supercapacitor requires a flexible and lightweight electrode materials to ensure the comfort and functionality in the wearable devices. means we are using for the human being or if any animal being. So we have to use this device, must be comfortable just to implant or just to wear. So functionality must be in the same sense whenever it will stretch or it may be. Moreover, it can work in the various environment like in the liquid, in the gas or liquid, in the any state it can work. So material such as carbon based material, metal oxide, metal carbide and nitride, conducting polymers and their compositions are typically used as the electrodes for the wearable supercapacitor. So there are the various groups which are working on these flexible energy storage devices, in which the zinc which produce the three-dimensional porous carbon material, which is using as a combustion technique. So the process involves the solvothermal interactions between the sodium and the ethanol, which creates a metastable solid that could ignite easily. So interestingly, the resulting 3D carbon became O-doped after adding the oxygen containing functional group to the carbon sheet surface. So to increase the specific surface area, concentrated acid was applied at room temperature to the unstable or the fragile area of the carbon material, which added the oxygen containing functionality group. So combustion products were submerged in the concentrated nitric acid to create the oxygen enriched 3D porous carbon. So the suitability of OPC, that is the oxygen enriched 3D porous carbon as a cathode for a zinc ion hybrid supercapacitor was investigated. So it was found to have the excellent capacitance performance. So now what type of the electrode materials we use for the supercapacitor? There are the various electrodes which we can use for the preparation of the supercapacitor. You can see on the screen there are the various like carbon, metal oxide, like nitride, like metal sulfide and so on. There are the various material. So we can use, they must be flexible, they must have a good functionality, moreover they must have a good function. So if we start with the flexible solid state zinc ion capacitor, that is also known as a ZIC, which show a high capacitance of 132.7, a high energy density and a high power density and at a current density of the 1. Now we are having, if we have a low current, then we can having a good. It is exhibited the superior cycling stability with the 87.6% capacity retention over the 10,000 cycles. So this is due to the 3D carbon porous networked structure that facilitates quick ion and electron transport as well as a large number of the functional group that containing the oxygen, which improve the pseudo capacitance. So we can see here, this is a galvanostatic charge discharge performance that we can have the oxygen enriched and more load is applied here. Right hand side we are having, that is a cathode side, that is the anode side, where we are having a zinc carbon cloth, and here we are having the left hand side the oxygen enriched porous carbon, that is a carbon cloth. So this is how we can get the charging faster. So again the zinc reported a self-powered stretchable system comprising a crumbled gold based triboelectric nano generator, that is TENG, that scramble graphene based string sensors and integrated in the micro supercapacitor array. That's why it is a MSCA. So it is another type where we are having the self-powered stretchable system. Now we can have all in one MSCA are built on the ultra thin ZNP nanosheets anchored on the three-dimensional laser induced graphene form and arranged in an Iceland bridge configuration. So that illustrates the construction process of the all-in-one stretchable MSCA. The ZNP at the rate of LIG electrodes are produced by spraying a coating of ZNP. We are having a electrode, then a ZNP will be coated on it over the LIG while using a shadow mark that we can see in the diagram. So after forming the 3D LIG form via pulse CO2 laser irradiation of the polyimide thin film and PVA KCl gel electrolyte drop casting is carried out. So lastly, the thin layer of the polydimethyl siloxane, that is PDMS, is utilized to enclose the MSCA. So the resulting hybrid electrode has reduced inactive material, a large ion accessible surface area, and excellent electrical conductivity due to the combined use of capacitive and Faradaic energy storage material. So as a result, all-in-one MSCA can deliver the high aerial, that will be the gravimetric energy density without compromising the rate capability or the cycling stability. So hybrid electrode with a large surface area have been found a possess excellent ionic and electrical conductivity. So these electrodes exhibit a gravimetric capacitance of 1425 Faraday gram inverse. So that is the 7.12 Faraday centimeter inverse 2. So so that will making them highly impressive. Additionally, they demonstrate the long term stability. So you can see here that illustrate the fabrication process of all-in-one stretchable MSCA's optical images of the serial and parallel configurations of MSCA both in a petri dish and on a human subject. So this is a very much interesting, and you can see the device fabrication by the various arrangements. So we can have the step by step functioning of the fabrication process of all-in-one stretchable MCA. Right hand side you can see at the hand of the human, that is a stretchable device, and now the petri dish is also having that devices. Now you can see easily on the human hand that it is stretchable. As we move the hand, these wearable devices flexible and move accordingly the force applied on it, and it works in a best manner. So on the screen we are having the various process. You can note down the various processes through this slide. So that is the illustration of the fabrication process of all-in-one stretchable MSCA, that is the optical images of the serial and parallel configuration of the MSCA both in the petri dish and on the human subject. You can see here there is a various parallel and series combination are here. So therefore it has been demonstrated that by carefully selecting the electrode material and the device architecture, stretchable micro power sources with a high energy density as well as significantly better rate capacity and specific capacity can be produced. Rate of capacity and the specific capacity we can produce by using this devices. So, they are more capable just to discharge at a long time. So, they will remain for a longer time. So, furthermore, the feasibility of a self-powered, well-integrated stretchable system is demonstrated by a sensitive and stretchable crumbled graphene based strain sensors. So, which is powered by the all in one stretchable MSCS prepared in this study. So, what we are doing, we are giving the energy to a sensor, we are giving a power to a sensor by using the MSCA. So, by using this device that has been generated and that can be used as a stretchable and wearable devices. Moreover, we are also having a stretchable sensor and we are having a flexible sensor. Along with this, the stretchable MSCA super capacitors are also attached and it will work in a good manner. So, another is the multi-layer composite electrode. How we prepare this multi-layer composite electrode? So, fabric electrode preparation by the screen printing and reduction, that also just taken from the research paper. So, that also they have worked on the multi-layer composite electrode deposition. So, they just prepare the fabric electrode by the screen printing and the reduction. So, again the zinc, that was one of the scientists who proposed a multi-layer composite electrode that is made of the copper nanoparticles. That's why it is called CUNPS, that reduces the graphene oxide, and it also uses the reduced graphene oxide, that is represented by the RGO, and the cotton fabric, that is the CU oblique RGO oblique CF. So, they prepare the multi-layer composite electrodes that is made of the various material in the 3-dimensional structure that show the process involved in the silk screen printing of the graphene oxide onto the fabric. So, we will further discuss in the next lecture how we will prepare the supercapacitor on the fabric. Thank you very much.